Today we find a very explicit formula for the Carnot-Caratheodory distance up to a universal constant. Previously, we used concatenation of two very specific horizontal curves to find the upper bound. In particular, we start at the origin, within the xy plane, continue to the projection of a point, and then we follow the horizontal lift of a circle to reach the point P. For this to happen, the circle must have the specific area of t over 4, which explains where the square root t comes in that formula. Now, in order to show that the distance is not much smaller than this quantity, we have to start with an arbitrary horizontal curve joining 0 to p, and then give a lower bound comparable to absolute value z plus the square root of t. So suppose gamma is some horizontal curve from 0 to p, and denote its projection by gamma bar and write it in coordinates in x as x and y functions. Now, what do we know about these objects? First of all, we know that the horizontal length of gamma, which is used in definition of Carnot-Caratheodory distance, is equal to the length in the plane of its projection. That we know. The second fact we know is that t is equal to twice integral over the projection curve of the form y dx minus x dy. And if you don't care about forms, in particular terms, this will be integrating over the domain of parameterization, the quantity x prime of s y s minus x of s y prime of s ds. And these are well-defined objects because gamma and its components are assumed to be absolutely continuous. And we vice versa know that if you have any gamma bar satisfying the second condition, its horizontal lift will provide a horizontal curve from the origin to P. So we're pretty much characterizing every possibility. Okay, so we said that in the case of P being on top of the original point, we were looking at loops. That's where we ended up finding the circle. But this is not per se a loop. However, there is a fortunate observation again. And this observation, notice, will depend on the fact that the first point is 0. This won't work with any other point. Look at the line segment joining the origin to z0. Okay? L, let be, say, an arc length parameterization of the curve that traces the segment in the plane, just Euclidean stuff, from origin to z and 0, the projection of point P. Then it's easy to see that x prime s y s minus x s y prime of s is 0 at every s. Because you're looking at 0, if you are at this point here, then the derivative, the velocity is also pointing in that direction. So the vector xs ys is parallel to x prime s y prime s, and because of the way we multiply this is actually dot producting the perpendicular to velocity into this, and they are perpendicular, so they become 0. And that means for free we can write this as 2 times integral over gamma bar followed by concatenated with this L. Okay, that's common notation in, say, algebraic topology. So if we add L, or maybe it's reverse, we don't change this integral quantity. But what happens is that now we have a loop. It comes back to origin. So this becomes again now the signed area. So the signed area cut out by gamma bar and the straight line segment L. Now we have the conditions, we can read them as follows. The horizontal length of gamma equals the Euclidean length of gamma bar, and we have the restriction that the area enclosed by gamma bar and the line segment must be T. In fact, this is -4 times, so let's add that to it. So technically that's -4 times that. But in any case, the point is that the area is prescribed by just point P. It depends on point P. The T, once it's fixed, it dictates what this area should be. However, we have so many options in choosing gamma bar. But now there comes the steep theorem, which we're not going to even state properly. So the isoperimetric problem solution, so let's say the whole theory of isoperimetric problem in R2 says the following. We will think of gamma bar as representing absolutely continuous curves in the plane. So among all absolutely continuous curves in R2, xy plane, that connect 0 to z, in this case our z and 0, and have this signed area equal to T over 4 in absolute value. So absolute value of that equal to that. The one where gamma bar is part of a circle, so it's an arc of a circle, has the least length or perimeter. That's why so it says that if you are in the plane and you want to obtain an area here, this signed area, if you want to obtain an area of T equal T over 4, the shortest length R2 gamma bar you can afford will be the one that comes from choosing this to be a circular arc. So if you go along a circular arc and connect to z and 0, and then join it to the origin, you will get T over 4, and this will be the shortest in terms of the length of gamma bar. And once you know this fact, it's easy to calculate how much length that will be. So the length of that circular arc will be comparable to length of z plus square root of t. So what I'm claiming is that if you have a circular arc from 0 to z, part of a circle, and this area is t, then the length of this part is bounded from below by such thing. So obviously it should depend on z as well, because what if t is almost 0? Then you will take basically this straight line itself. And then you cannot, of course, have 0 on this side, because you still need to travel from 0 to z, which amounts to this much. But anyway, none of this we have given proof of, but at least I'm explaining where this quantity, the lower bound, comes. So gamma bar, in the most optimal case, will have the lower bound of this much. So if it comes from projection of an arbitrary horizontal curve, in particular, this will also satisfy that inequality. So all in all, we conclude the following theorem: for any horizontal curve from 0 to z and t, the length of gamma is bounded below by a universal constant. So this wiggly sign, that means there is a constant c, not depending on z or t at all, so that this is more than c times absolute value of z plus square root of t. And because remember, dcc is infimum over all such length, and this side does not depend on gamma, we will also get the same inequality for dcc, which together with the upper bound proves this. Corollary, there exists some c bigger than 1 such that for every point z and t, Carnot-Caratheodory distance of 0 and p is 0p is bounded from above by c times absolute value of z plus square root of t, and from below by 1 over c times absolute value of z plus square root of t. The end of the story. So this gives, up to a constant, a very good understanding of how distances behave in Heisenberg group H1. Remember that we have avoided any mention of the group structure of the Heisenberg group, and that makes it difficult to talk about the Carnot distance of arbitrary points. Once we do learn about that group structure and the left invariance of this distance, we will see that this must be equal to multiplying from left by p inverse, so that will be 0, and then p inverse q. And therefore, knowing distances to 0 gives us distances between any arbitrary points. But again, that relies a lot on left translations in the group. And that will be the topic of the next chapter on Heisenberg groups. If you have any questions and comments, please leave them below, and see you in the next lecture.